Hello and welcome to another ICMonitor tutorial. Today we'll talk about generic nodes and how you can use them to represent your own protocols and data in the ICMonitor. We will introduce nodes, and by extension generic nodes, configure generic nodes using an example that's easy to follow along, and put them to use using the ICMonitor analysis features. To start, we have to answer two questions. The first being, what are nodes in the ICMonitor? And the second, what are then generic nodes and what are they used for? Nodes in the ICMonitor represent fields in protocols. And we can see them in the nodes view over here. So if we take a look at a well-known protocol like IP, we can extend it and we'll see it has some fields underneath. It has a header that then has nested fields in it. And it has, for example, flags that describe what the individual bits in the flags do. Everything in here is a node, and nodes can have parents and children. Now, what are generic nodes? The ICMonitor brings with it a lot of nodes of protocols that it already can translate and analyze, most notably the TCP/IP stack or whatever analysis function you acquired with your license. And generic nodes are nodes that you can describe yourself. So they can be used to analyze a proprietary protocol that you're currently developing, where the ICMonitor has no protocol knowledge, but you can describe it with its offsets and its length using generic nodes. It can be used to analyze, for example, the bug output that you have of an embedded device using a serial port, where you can make sense of the individual flags or bytes and just quickly hack together a protocol that you can then analyze in ICMonitor and make your debugging a lot easier. It can of course also be used to analyze data inside of well-known protocol fields. For example, if you have cyclic data analyzing an industrial network, you can then use generic nodes to describe structured data inside the data fields. Now that we have a concept of generic nodes and what they're useful for, let's go ahead and configure them. You will find generic nodes in the Configure tab in the Nodes and Scripts section. We'll click on Generic Nodes and open the Generic Node Configuration dialog. Here we can add nodes and their children and nest them as deep as is necessary to represent our protocol. We can of course remove nodes, and be mindful, if you remove a node, all the children will go with it. So always check for the little arrow and expand it and double check. To make a node usable, it has to be configured, which is done on the right-hand side of this dialog. We'll select the node that we want to configure by clicking on it, and then start out with its general description. As part of that, the node has a name and a short name, which is used to identify it in the graphical user interface. We then pick an abbreviation in which we can use small letters, numbers, and concatenate words with dash or underscores. If you use letters that are not permitted or special characters, the field will turn red to warn you. Abbreviation must be unique in their space, meaning if we add more nodes, we must make sure that each one has a unique abbreviation on this level. We can repeat the abbreviation in child nodes, but then the child node has to be unique on its level. You don't need to be concerned with existing protocols because all generic nodes live underneath a generic root node. We can then pick a description, but that's optional, and we pick which type of node we want to create, though for the top level only byte nodes are available. If we need to repeat the same node back to back, we can use the create clones function and just pick the number of clones we need and the starting index. To make sure abbreviations stay unique, we can then use the %i to substitute in the node's number. So if this is clone number 5, it will say N15. We can then define filter expressions, which are used to determine if the node contains data. We'll see that more clearly once we configure our little example. The main factor in determining the data of a node is the parent node. So we can pick from the list of all the known nodes in the IC monitor. For example, in the Ethernet and the payload. And our node will then contain data when Ethernet has data, which in the IC monitor is mostly every telegram. After the general description, we can then configure offset and length. It'll either be done automatic by the sum of these child nodes and their predecessors, or we can put a fixed number for both of these values. To pick the way data is being interpreted, we can do that in little or big endian. If we add child nodes, we have the further option of making them bit nodes. Bit nodes pertain to the data of the parenting byte node, and we can then define individual bits. Usually you'll have fixed offsets in here and fixed bit length to represent flags or very small fields of data. Of course, we can also have byte nodes as parents and children, and have a bit node underneath those. Don't worry if those are a lot of settings to memorize. It will make a lot more sense and become more intuitive once we put them into practice. So let's start with our example, and we're going to simply recreate a part of the IP protocol. So we're going to go to the top node and give this a name, a short name, which can be the same, and an abbreviation that's unique. I'll fill in a description as well, and we'll leave byte node because we don't have a choice in this case. Now let's define a filter expression to make sure that our IP nodes only have data when they're actually present in the telegram, and IP is identified by the Ethernet type field. So if we go in here, say we want to go to the Ethernet node and its type field, and it must equal hex 800, our node will only have data when IP is part of the Ethernet frame. We'll now pick our parent node, which is the Ethernet service data unit, and configure offset, but leave the length to automatically be calculated by the sum of its child nodes. So looking into the Ethernet node, we'll have a destination and a source, VLAN tag and type. If we add those up, it leaves us with an offset of 14 bytes. And there we go. That constitutes our top-level IP node. Now let's add some subnodes, and lucky for our demonstration purposes, the first couple of subnodes are already bit nodes, which are the version field, which has a length of 4 and an offset of 4. We then add a second child node, which is the Internet header length. Also make this a bit node, and it also has a length of 4. Now if we add our next node, we'll notice, since we have 2 bit fields with a combined length of 1 byte, we have an offset of 1. Now we'll use the next node in the IP protocol, which is the type of service field. The type of service has 2 components, one being the SCP, with a length of 5 bit, and the other one being ECN. For the remaining 3 bits. Now let's add the total length, which is a length of 2. And there we have a basic representation of IP. Of course, there are many more fields, and we might add one more that is interesting and easy to test, which is the TTL field. But we have to put the offset here manually. Should be 8 bytes and 1 byte of length. So now we have a couple of fields. Not all have to be concatenated, but if we add fields that have a further distance to the generic IP, then we have to put in the offset manually. Now, before we hit apply and test our generic nodes on some actual live captures, let's go over the settings and see if they make sense. I want to start with the top node, as I put in a mistake there to highlight a concept. We configured a fixed offset of 14 bytes, and we pick a parent node, the Ethernet service data unit, which is a wrong configuration because the service data unit already is the payload, so we don't need the offset. My argument was, we have a destination, a source, and the ether type, which amounts to 14 bytes. In some networks, though, we also have the optional VLAN tag, and we can't really account for this with generic nodes, as we cannot put in dynamic length. So for most known protocols, the IC monitor offers you to just pick the service data unit, and then no matter what the offset here is, the monitor will adjust for it, and your IP packets will be correct. So now we fix this. The second problem in quotes is that we have a total length, which is a field of 2 bytes of length, so we need to account for endianness, and IP is sent in network data order or in big endian. So we need to switch this for transformations into data types like unsigned integer to be correct. For all the other fields we configured, we only have 1 byte of length, so it doesn't really matter if it's little or big endian. Now with this out of the way, let's hit apply, go to the capture, and test out our nodes. The easiest way to generate some telegrams to test out our generic nodes with is to just ping a device in the network. To make sure we also get some telegrams in there that do not contain IP node, I cleared the ARP cache, and if we then ping a device we didn't yet talk to, we're guaranteed to get some ARP requests and responses. So let's pick a capture interface, preferably one that's IPv4 enabled, and start the capture. We'll then go ahead and ping a device, and stop our capture, as that is enough data to work with. Now one use of the generic nodes, if you pick a random packet in here that contains IP, is that we can just inspect the fields we configured and the telegram details. Now to test the filter, we'll put a filter condition in here, and we want the ether type to not be equal to hex 800, meaning it doesn't contain IP. So we get a couple of ARP telegrams in here, as promised, and if we now open the generic nodes, they're empty, because they don't contain data, because we don't have IP on this protocol stack. So now let's look at our ICMP and see the generic nodes. We can also use the generic nodes in the Telegram list view by just pulling them up here, like we would any other Telegram node. Let's for comparison get the matching IP fields in the original, which would be the total length, if I can find it. There we have it. And the TTL, and rearrange that So we have a match. Now, as we see, all generic nodes have hex as their base display format. But to do a comparison, we can change this to unsigned decimal. Now we can compare the TTL fields. And for the total length, which is a 2-byte field, we'll just go to 2-byte. And there we go. Now rearrange this a little bit, and we can see we configured our generic nodes properly, but we more importantly see that we can use generic nodes like any other node in our Telegram list. We could also use it for filter conditions. We could either go up here, pick the generic node root node, and use autocompletion to get to the fields we need. For example, our TTL. We can then say we only want to see all TTL fields that have a value of hex 80, which equals 128. And there we go. We have our 4, I think, requests. Yes, the 4 ICMP requests. Now, if we clear this condition and pick one with a TTL of 64, we can also get filter conditions from right here. Right-click it, say Telegram expression, concatenate it with and apply. And now we should get all our replies. So generic nodes behave pretty much like any other node. Can be used with Telegram expressions. We could, of course, also use them in filters. And we can also use them from the dialog down here. Now, if we have a colleague that should analyze our proprietary or debugging protocol that we currently have configured with generic nodes, we can go to the configure and export the active configuration, which will just export the settings that we did in configuration. And be sure to have the generic nodes plugin checked. We can then export. Of course, we can also just go to File, say Export, and export everything else with it as well. The latest configuration will persist, so if you close and reopen the monitor, you won't lose your generic nodes. Now this concludes our tutorial. I hope you learned something, and we'll see each other in the next tutorial.